some of the concepts that we've been covering for the past several lectures now. So I'm going to try to go over slides that reinforce what we've been doing while also teaching you something new along the way. So we were talking about acids and bases the last time. So let me start by showing you a very classic reaction that happens in aqueous solution when you mix acids and bases. And then we'll use this as an opportunity to refresh your memories on the net ionic equation, which of course you had a full lab on that last week. So in a classic acid-base neutralization, here's an acid, hydrochloric acid, and here's a base, sodium hydroxide base. And when you mix these together, you get two classic products out. You get a salt of the acid. In this case, the salt is a salt that you're very familiar with. In fact, we call it common table salt, NaCl. But there's lots of different salts. It depends on what the acid and what the base is. NaCl happens to be the salt of hydrochloric acid. And water is the other product that you get out here. Right, so this is what we would call, in our context of the net ionic equations that we did at the beginning of this chapter, right? This is the molecular equation. This describes, this is our shorthand of the chemical reaction that's taking place. But if it's an aqueous solution, that really means that these materials are dissolved in aqueous solution. And when they dissolve, these are ionic compounds, they dissolve and further dissociate into their component ions. So like we did before, I'm going to show these drawn in their ions that are in solution. By the way, we first need to make sure that the equation is balanced, but it is. So that's why I didn't balance it already. All right, so now we're describing the full ionic equation. These are the ions as they actually exist in solution. Sodium hydroxide splits into sodium ions and hydroxide ions. Sodium chloride on the product side will dissociate into sodium ions and chloride ions. But water on the product side, that's liquid. It's not listed as an aqueous solution. So those don't split. That stays together as a covalently bonded molecule in solution. So this stays as liquid H2O. So now when we look at the full ionic, we can recognize which are the spectator ions. Those are the ones that are present both at the beginning of the reaction and are present in the same context and the same molar amounts in the product side. We have chloride ions in aqueous solution in the reactants, and we have chloride ions present in the products. So chloride ions are spectators, and sodium ions are spectators. So we can cross them out, but let's notate that these are the spectator ions. In this case, they're sodium ions and they're chloride ions. What's left over is, of course, the net ionic equation. That's going to be hydrogen ions in aqueous solution plus hydroxide ions in aqueous solution will come together and form H2O molecules, liquid. That's the net ionic equation. And in fact, all acid-base chemistry, at the heart of it, I shouldn't say all, but most acid-base chemistry, at the heart of it, has this as the net ionic equation. This is really the only chemistry that's happening in the context of this acid-base neutralization reaction. So in fact, by the term, what's being neutralized here is the charges, the hydrogen ion charge and the hydroxide ion charge. So when we say neutralization, that's what's being neutralized. When they come together to form the molecule H2O, that's a neutral molecule. So to refresh your memory now on what we did back in chapter, you can overlay, for example, a theoretical yield question for something like this. And here is one, right? We're spilling 20 milliliters of 3.5 molar hydrochloric acid in the lab. What volume of 5 molar sodium hydroxide is required to neutralize the acid? Now we could go back and do it the old-fashioned way, focusing on the molar amounts of the reactants and the molar amounts of the products, and do a theoretical yield. But let me show this to you in a slightly different way. Let's do this in the context of the net ionic equation. We know that this is really what's happening. And we know now from discussing acids and bases what they produce in solution. So the acid's going to give us the hydrogen ion in solution. The base is going to give us the hydroxide ion. And we know that that's how they are going to neutralize each other in solution. And we want to add just enough base to neutralize the acid that was spilled. So let's find out how much hydrogen ion actually needs to be neutralized in the amount that was spilled in the 20 milliliters of 3.5 molar HCl. So this is going to be a review for all sorts of things: concentration, going from volume to moles and moles to volume and stuff like that. So let's start with our volume. We spilled 20 milliliters of HCl, but our molarity, remember the units of molarity are moles per liter. So I'm going to put that milliliters in liters, which I'll just do that in my head. All right. This is 0.020 liters. That's the same as 20 milliliters. If you don't know what I did there, you better come to office hours and I'll explain it to you. But that puts the volume in the units of liters. I'm going to then use the molarity to convert from liters to moles. The molarity is 3.5 moles of HCl per liter. Okay, that's the molarity. So here's the volume. Here's the molarity. Now that would give me the moles of HCl, but I want to know the moles of hydrogen ion. So I'm going to formally put one more term in here just so you can see how the units cancel out. I'm going to show that for every 1 mole of HCl that's in solution, it produces 1 mole of hydrogen ions in solution. Numerically, that's not going to change our answer, but it is going to put the units in what I want, which is moles of H+. So let me just demonstrate that to you, that our units cancel. Liters cancels with liters. Moles of HCl cancels with moles of HCl. And that leaves me with moles of H+, which is what I want. So if I do that math, well, I don't need a calculator. That's 2 times 3.5, which is 7. But I need to keep track of the decimals here. So that's going to give me 0.070. That's moles of H+. That's what was spilled. That's what needs to be neutralized using our net ionic equation. But using that net ionic equation, we now know that for as many hydrogen ions that we have that need to be cleaned up, we need the same number or the same number of moles of hydroxide ions. So when it's neutralized, this is going to equal the same number of moles of hydroxide ion, 0.070 moles of hydroxide ion. This is what's needed to neutralize the spilled acid. So now I can use that to start a new term. I need 0.070 moles of OH minus. Where am I going to get it from? Well, I'm going to get it from the 5 molar NaOH. Now, NaOH, that's a strong base. So for as many moles of NaOH I have, I'm going to have the same number of moles of OH minus, because remember, it dissociates 100% in aqueous solution. It's a strong base. I'm telling you, it's a strong base. But I also told you up above the other day that metal hydroxides form strong bases. See, here's sodium hydroxide. It's a strong base. So let's show that with dimensional analysis. Every 1 mole of NaOH that I have in aqueous solution, that's going to produce 1 mole of hydroxide ions in aqueous solution. But I've put the units the way I have here so that they cancel out. Right? I start with moles of hydroxide ion. That cancels with moles of hydroxide ion, and I'm converting that into moles of NaOH. And where am I going to get those moles from? I'm getting them from the 5 molar solution. So molarity, moles per liter. So let's put our units in. That's going to be moles of NaOH per liter. That's the molarity. And in this case, it's the inverse of molarity. Okay, it's 5 molar. So that's going to be 5 moles of NaOH per 1 liter. Now I can calculate how much volume of that 5 molar NaOH I'm going to need. Now for this one, I'm going to need my calculator because it's 0.07 divided by 5. 0.07 divided by 5. And that gives me 0.014 liters of 5 molar NaOH. Or if I wanted to put that back into milliliters, that would be 14 milliliters. That's how much is needed to neutralize. Okay, so that math should look familiar to you, although it's done in a different way. This time I'm doing it in the context of the net ionic equation that happens in an acid-base neutralization. But it's the same kind of manipulations if you're using stoichiometry, like when you were calculating how much carbon was in ammonium bicarbonate or sodium bicarbonate. When you did that lab, you got that from the moles of carbon dioxide that left your system. It's the same math. All of this is the same math. So I like showing this to you in a different context because that way you can see how you can learn how to use a tool in different capacities rather than just memorizing, oh, I know I need to convert from grams to moles and then moles to this, moles to that. And if all you do is memorize that mechanical process, then the minute you're faced with a problem that does things in a slightly different way, you get lost. All right, so these do get a slightly more complicated, not really, but if you have, say, a different kind of acid that produces more than one hydrogen ion to solution. We talked about diprotic acids yesterday. So if we had carbonic acid that was spilled, we'd have to take into account the fact that there are 2 hydrogen ions produced for every 1 mole of carbonic acid that was spilled, as opposed to this term here, that was only 1. So I might need to replace that term. Or maybe the base that I'm using, maybe the base is barium hydroxide. Or maybe the base is aluminum hydroxide, which looks like this. So now that term is going to change. Instead of 1 to 1, right, I would write that for every 1 mole of barium hydroxide that I have an aqueous solution, that's going to produce 2 moles of hydroxide ion, et cetera, et cetera. Okay. Now, for the sake of time, I'm not going to go through all of these slides because this one just basically takes you through that barium hydroxide example in exactly the same way that I did before, except now we have barium hydroxide as a base instead of sodium hydroxide. So I'm not going to solve that problem for you, but let me just remind you of the steps that are involved when you do something like this. You recognize that this is an acid, or I tell you that's a strong acid, and I tell you that this is a strong base in a problem. So you don't need to worry about whether they dissociate 100% or not. If I tell you it's strong, that means it dissociates 100% into its component ions. But now the right-hand side is blank. The product sides are blank. So you have to recognize, all right, well, this is an acid-base neutralization. I know that I'm going to get a salt of the acid and water. Well, in this case, what's the salt? Right? This forms chloride ion in solution, and this forms barium cation in solution. So that's going to be our salt. We're going to have the barium cation paired with the chloride anion. But you can't just stop there. You have to go back to the skills that you learned earlier in the semester and say, all right, this is my new cation-anion pair. When I write the molecular formula, I need to make sure that that pairing is net neutral. That's what a formula unit is. Remember, the formula unit for an ionic compound is the net neutral pairing of cations and anions in that compound. So we need that ratio to be correct. Well, you look on your periodic table, you'll find that barium is in group 2. Or you look here on the left-hand side, barium hydroxide comes with 2 hydroxide ions for every 1 barium cation. And you should know by now that the hydroxide anion is OH minus, 1 minus charge. So you know that that barium is a 2+ charge. And the chloride ion you should know, or you know how to look it up, is a 1 minus charge. So this, as a compound, is BaCl2 in aqueous solution. So you got to do that step as well. And then, of course, we're making H2O as the other product. But now you need to make sure the equation is balanced. And you know how to do that from chapter 7. We have 2 chlorides on the right and 1 on the left. So we need to put a 2 here. And that gives us 2 hydrogen ions on the left. Now, we don't have hydrogen ion on the right. So it's a little trickier to balance these. But if you go back to the net ionic equation, what's really going on here? It's H plus OH minus gives us H2O. Think of it as HOH, okay? If you think of it that way, then the partnering is very simple and the balancing becomes much more simple as well. If this is HOH, well, we have 2 hydroxides and we have 2 hydrogens, so we need a 2 there. So we put a 2 here. See, visualizing it that way makes it a little easier. In fact, this is a double replacement reaction. Think of it this way. And it sort of is, except we're now not all ionic compounds. Now, the HOH is really a covalently bonded molecule, but you can think of this as a double replacement as well. So acid-base neutralization reactions are also double replacements. Here's A, B, C, D, and that gives us CB. And really, this is AD. It's just now in the context of a covalently bonded molecule. But thinking of it that way helps you balance things pretty easily. So now that it's balanced properly, I'm going to bring those coefficients down to the full ionic equation. So this is now 2H plus and 2 Cl minus gives me plus 1 barium. But now we've got, look at this, this is 2 hydroxide ions for every 1 barium cation. So when that's dissociated in solution, it dissociates into 1 barium 2 plus and 2 OH minuses. Okay. Here I've got the 2, that gives me a 2 here and a 2 here. Many of you didn't keep perfect track of this in your lab exercise last week when you were practicing doing lots of net ionic equations. You got to pay attention to all of these steps. All right, now when we recognize the spectators, they're going to be pretty much the same, except the salt is different, but the salt is the spectator ions. And what's left then is 2H plus 2 OH minus goes to 2 H2O, which of course whittles down to 1 to 1 to 1. Okay, so we're back to the same net ionic equation that we started with for the acid-base neutralization. This is acetic acid. This is a weak acid. Acetic acid. This is weak. And we're now mixing that with a strong base. Now, from the molecular formula, the molecular equation, we still have the same 2 products. We have a salt of the acid. In this case, the salt is called sodium acetate. And you may recognize that the acetate is one of those polyatomic ions that's on your polyatomic ion list. Here's the acetate ion. It's CH3COO minus. And of course, we have water. Is this one balanced? Yes, it is balanced. Okay. So we could go ahead and pull this into the full ionic equation and the net ionic equation and whatnot, but it's a little more complicated than that. So as a weak acid, let's just go down here at the bottom. As a weak acid, we don't get complete dissociation of acetic acid into its component ions. This is one of those equilibriums that I told you about before. This arrow goes both ways. All right, we don't run this reaction to completion. It's an equilibrium. So when you put that in aqueous solution, you have the acid is there, and you have these components there as well. It's all present. Now, sodium hydroxide is a strong base. This goes 100%. So as much sodium hydroxide that you put in solution, all of it dissociates into hydroxide ion. And once you have hydroxide ions in solution, they're going to merge with the hydrogen ions in solution. That's the net ionic equation. That's going to go ahead and give you the water. So even though the acetic acid doesn't completely dissociate, as soon as the H plus reacts with the OH minus, now there's no more H plus over there, and more of the acetic acid is going to dissociate further into its component ions until eventually all of it gets reacted with. That's another thing that you're going to learn more about in second semester chemistry for those of you who take it. But when we show this in aqueous solution, though, the full ionic looks like this. It's a little complicated, okay? But the full ionic, well, we don't have the acetic acid completely in ions, all right? It's weak. So the full ionic looks like this, CH3COOH. It's still an aqueous solution because it's weak. But that also means that on the other side of the reaction, we still have its component ions, CH3COO minus and H plus. So that's just showing you the weak acetic acid by itself. The sodium hydroxide, though, is strong. So sodium hydroxide, let's just put that in a different color, plus hydroxide ions. And then over here, we have sodium acetate. So that's also going to give us sodium ions in aqueous solution. Here, I need to give myself a little bit more room here. Plus the acetate ions. And then we have H plus and we have the OH minus. We're going to have the H2O because, sorry, I shouldn't have split this up here. This is still going to be H2O. So when you're looking at the net ionic now, we formally write this then as the acetic acid is still present in aqueous solution because in the net ionic, it's not completely dissociated, right? It's a weak acid. But the sodium ions, these are spectators, okay, because they're present on both the reactant side and the product side. This is now what's left over. And on the product side then, we have the acetate ion in aqueous solution, and we have the H2O. It looks a little more complicated. The reason we can't distill the net ionic equation down further is simply because this is a weak acid. So what we're showing is that in the net ionic is we're only showing the partial dissociation of the acetic acid. Although ultimately, as I've shown you down below, ultimately, as long as you keep adding a strong base there, it will all go to completion in the very, very end. And you will, in the end, get down to the same net ionic equation that I started with because of this that I'm showing you here in blue. But this is formally how we show the net ionic equation. In this case, for a weak acid reacting with a strong base, right? You show that the weak acid is only partially dissociated. But because of this, all right, ultimately, all of this reaction is going to go to the hydrogen ions and the acetate ions in solution. So ultimately, we are going to end up with this CH3COO minus plus H plus. And then, of course, the base was the same. And then here we have the sodium acetate, what I showed you above, plus the acetate ion. And then plus H2O liquid. I should have written ultimately here. Ultimately, this is still happening because the acetic acid isn't alone in solution. You're adding a strong base to it. And every time you add strong base to it, this is happening, which means we're drawing the acetic acid completely into its ions. So in the end, we are going to have sodium ions still as a spectator. And now we can cross out acetate ions as a spectator as well. And we're back down to H plus OH minus forms H2O. It's still at the heart of the acid-base neutralization. I just wanted to show you this one more difficult example when it's weak. When it's weak, we actually describe the net ionic reaction showing that it's weak. So chew on that for a little bit, okay? Again, I recognize that that one's a little more tricky to understand. But instead, I want to go ahead and talk about the next to the last subject in this chapter, which is also something that you started learning about in the context of your laboratory exercises, and that's reduction and oxidation, or what we call redox. It has to do with the gain and loss of electrons in chemical reactions. And you've learned about this all semester long, way back when we started understanding why ions formed in the first place. Back when we were, showing things that were isoelectronic with their nearest noble gas, and being able to predict that fluorine will gain 1 electron to become the fluoride ion, or sodium will lose 1 electron to become the sodium plus cation. Those are oxidation reduction reactions. So just to formalize how we define these, oxidation, right? That's going to be the loss of electrons. And reduction is the gain of electrons. Now, when we get later on in this subject, I might even start to show you why it's called reduction and why it's called oxidation. But for now, let's just concentrate on the definition. That's the formal definition. That's how we use it today. And I'll show you some examples of this. Actually, let's just work with this right now. Here's solid magnesium is reacting with chlorine gas to give us magnesium 2+ ions in aqueous solution and chloride ions in aqueous solution. Is this balanced? It is not balanced. How do you want to balance it? Add 2 chloride ions. Now it's balanced. Now, magnesium solid and chlorine gas, that's how you find them in nature. Metals, as you find them in nature, solid metals, they are neutral. Gases, as you find them in nature, chlorine gas, as you find in nature, as a diatomic molecule, but it's neutral. As you find things in their natural environment, they are neutral. So I'm going to emphasize that by putting a 0 where I would normally put a charge here, okay? Now what's happening here? One of them is losing electrons and one of them is gaining electrons in this reaction. Who's losing the electrons? The magnesium is losing the electrons. How many electrons in this balanced reaction is magnesium losing? lose? 2, yes. This loses 2 electrons. How many electrons are being gained? And who's gaining it? It's something's got to gain it. It's the chlorine, right? The chlorine gas, how many electrons are being gained here? There's 2. Each chloride ion has only gained 1 electron, but in the balanced reaction, we have 2 of them. So now you're going to start to see when we balance a reduction oxidation reaction, we're not only using coefficients to balance the atoms, we're also going to be balancing the electrons, okay? Nothing is being lost or gained. Conservation of mass, conservation of energy. But now we're going to be keeping track of the electrons as well as they're moving around. We can describe this as what we call 2-half reactions, because for one thing, to lose electrons, magnesium is not going to give them off to thin air. Magnesium is only going to lose those electrons if there's something else there that wants to gain them. It still takes energy to get electrons to leave magnesium. Remember that ionization energy that we talked about earlier in the semester. They won't just leave on their own. Now, chlorine has a high electron affinity. So that actually provides the energy necessary to get the electrons away from the magnesium atoms. So let's describe then what's happening. Let's just describe the reduction part and let's describe the oxidation part. And that will also help us keep track of the electrons, okay? So this is the magnesium is being oxidized. And let's just show that formally. We have magnesium solid, which is neutral, is being oxidized. It's going to turn into the magnesium 2+ cation in aqueous solution plus 2 electrons. There they are. The reduction part, well, chlorine is being reduced. So the chlorine atom is reduced. And in this case, we have chlorine gas, that's neutral. Well, we need 2 electrons to reduce both atoms of chlorine to produce 2 chloride ions. So here are the 2 electrons, and that's going to give us 2 chloride ions in aqueous solution. So like I said, these are what we call 2-half reactions. The oxidation half and the reduction half. You can see that 2 electrons here cancels with 2 electrons here. So what we end up with is the reaction that we started with, but I'll just write it down here again. Magnesium solid, that's neutral, plus chlorine gas, that's neutral. Will undergo an oxidation reduction reaction to produce magnesium 2+ cations in aqueous solution and 2 chloride anions in aqueous solution. And I don't need to show the electrons because they've canceled themselves out. But by showing it to you in the half reaction, that actually keeps track of the electrons. All right, so oxidation is loss of electrons or lose of electrons. That's what I wrote. Loss of electrons. Reduction is gain. In lab, you learned a real neat little mnemonic device to remember which is which. Anyone remember what it was? Oh, did you say Leo the lion says grr? I hate that one. No, I just don't like that one. Yeah, you can use Leo the lion says grr. Leo the lion says grr. So loss of electrons is oxidation. Gain of electrons is reduction. I don't like that one as much as oil rig. Oxidation is loss, reduction is gain. But you, my friends, can use whichever one you want to remember which one is oxidation and which one is reduction. And again, that's just by following the electrons. There are other older definitions of oxidation and reduction. And let me just list some of these for you. I might refer back to these later on. You'll find that if a material gains oxygen, as the name implies, That's also oxidation. If you're adding oxygens to a molecule, you're actually oxidizing the atom that the oxygens are being bonded to. And we will take a look at that, probably on Wednesday. It also turns out if you're doing reactions and you end up losing hydrogen in a reaction, that also ends up being oxidation. For you biology majors out there, when you do, when you metabolize glucose, you're taking hydrogens away from glucose. You're oxidizing the glucose when you do that, okay? And then the reverse is true as well, right? If oxidation is gaining oxygen, well, if the molecule loses oxygen, that's also being reduced. The molecule is being reduced. And if you gain hydrogen, you're also being reduced. But let me put these in parentheses, okay? Because we're staying focused on what's happening to the electrons in our definition here. All right, let's do another example. Let's do aluminum mixing with oxygen gas is going to give us aluminum oxide, okay? And this time, I'm not going to balance the reaction first. Let's do this instead by looking at what happens to the electrons. And in balancing the electrons, you'll see that it will end up balancing the equation. Now, it's a longer way to do it, okay? So if the task was, let's just balance this reaction, you know how to balance the reaction. In fact, let's just do it real quick, okay? You could probably already do it in your head. There's 2 aluminums here, so we put 2 aluminums here. We've got 3 oxygens. Oh, let's not start, well, we have no choice. We have 3 oxygens on the right and 2 on the left. How do we deal with that? Well, the oxygen on the left is isolated, so we can use our fraction trick, right? How do we use the fractions? How many oxygens total do we need on the left-hand side? 3. So what fraction are we going to use? 3/2. And now let's get rid of the fraction. So the 2 goes away. So that makes this a 4. That leaves that as a 3. And that puts this as a 2. And so now we're balanced. Okay, 4 to 3 to 2. But I'm going to erase all that, okay? Because I want to now show you this by balancing the electrons. So let's write what the oxidation half reaction is here. What's being oxidized? Can you tell? Is the aluminum or the oxygen being oxidized? The aluminum is being oxidized. You can tell a number of ways. Here's an ionic compound, right? What's the charge on the aluminum cations here? 3+. And what's the charge on the oxide ions? 2-. Also, by the definition I just told you up above in red, if it gains oxygen, it's being oxidized. Well, look what's happening to the aluminum in this reaction. It's gaining an oxygen. So in effect, the aluminum is being oxidized, okay? So let's write then what the half reaction is. So aluminum is being oxidized. So we're going to start with aluminum solid, and it's oxidized. It's going to form the aluminum 3+ cation, and then 3 electrons. Let's just write them there. Okay. The reduction half reaction. Well, there's only one other thing there, so the oxygen must be reduced. So we're going to have oxygen gas that comes as a pair, O2. So that means I'm going to have 2 oxide ions in the products. How many electrons do I need to do this? It's 4. Okay. So there's the half reaction. But now I don't have the same number of electrons. One of them, the oxidation, only has 3 electrons, and the reduction half reaction only has 4 electrons. So what can we do to balance the electrons so that we obey the conservation of mass when we do this reaction? Use the least common multiple. And what's that going to be? The least common multiple between what? Between 3 and 4. So what's the lowest common multiple between 3 and 4? Let's see, 3 times 3 is 6, but that's not a multiple of 4. Times 9, yeah, it's 12, right? 12 is the lowest common multiple. So to get to that 12, I'm going to multiply across all of this one by 4. That's going to give me 12 electrons. And I'm going to take this one and multiply across by 3. In both of those cases, that gives me 12 electrons. So let's write that down below here. So that's going to give us, let's do the oxidation. That's going to give me 4 aluminum atoms will become 4 aluminum cations plus 12 electrons. And the reduction side, I'm going to have 3 oxygen molecules pick up a total of 12 electrons. And then that's going to give me 6 oxide anions. Yeah, question. These are still half reactions. I left the states of matter off. It's okay. You can just track them down. This isn't a solid. I'm just trying to keep it simple for now. Here, so it's not too confusing. Let's just. Okay, so these are still half reactions. I'm just scaling them so that we can balance the number of electrons. Now that they're balanced, we can add these up. Okay, the electrons go away, and we end up with then 4 aluminum. Here, now I'll put the states of matter back in for you. Okay, 4 aluminum atoms plus 3 molecules of O2 gas will react to give us 4 aluminum cations and 6 oxide anions. Now, to complete this, though, we have to recognize that these cations and anions, this isn't a solid. These aren't an aqueous solution, okay? If it was an aqueous solution, I would leave it this way. But these are solids, meaning that they don't separate. As a solid, they're together in an ionic compound. And that ionic compound, we know, has the stoichiometry of Al2O3, right, as a solid. So how many of those? It's 2 of those, right? That's 2 Al2O3. That gives me the 4 aluminum cations and the 6 oxide anions. Everyone see that? And so indeed, we do now have the balanced equation. Let's put it back up here. It's 4 to 3 to 2. Now, again, I don't recommend you doing it this way necessarily if you're under a time constraint, but it's very, very informative to show you what's happening with the electrons in a balanced reduction oxidation. So it is a useful skill to know how to balance these equations using the half reactions. Okay, if I were to just challenge you to balance an equation without getting into whether it's a reduction oxidation or not, you're on your own to balance it however you want. But I do want you to understand what's happening here in a redox type reaction. Let's take a look at this one. Here we're starting with the net ionic equation. Take my word for it. Maybe on Wednesday, I'll work it backwards from the full equation and prove to you that this is the net ionic equation. But let's say that's a net ionic equation that we're going to work with here. And let's go ahead and balance this. The challenge is to balance this reaction. How many of you think this is already balanced? Kind of looks balanced, doesn't it? We have 1 iron on the left and 1 iron on the right. We have one. What's PD stand for? Palladium. It's not platinum. Platinum is PT. We have one palladium on the right and one palladium on the left. So is this balanced? Who thinks it's balanced? You all know me by now, right? I don't make it that easy. Why is it not balanced? Because what? Because of the charges. All right. We have the palladium is 2+, the iron is 3+. This is not balanced with respect to the electrons, even though it looks balanced. So let's balance this the way I just showed you how to do it. Let's look at the oxidation half reaction. What's being oxidized here? The iron's being oxidized. So let's just write that in. So iron as a solid is 0, and it's being oxidized to iron 3+ plus 3 electrons. Okay. Then that means the palladium's being reduced. We're starting with palladium 2+, and we're going to palladium solid. So we're picking up 2 electrons to give us palladium solid. We need to balance this. So what's the lowest common multiple between 2 and 3? 6, which means we're going to multiply this one by 2, and we're going to multiply this one by 3. That's going to give us 6 electrons each. So now we have 2 iron solids will be oxidized to give us 2 iron 3+ cations plus 6 electrons. And on the reduction side, we're going to have 3 palladium 2+ cations are going to pick up a total of 6 electrons to give us 3 palladium solid atoms. Okay. The 6 electrons cancel out, and we end up with, we end up with 2 Fe solid plus 3 palladium 2+, undergoes a reduction oxidation reaction that gives us 2 Fe3+ and 3 palladium solid. Okay, so now we can balance the net ionic equation up here. It's indeed 2 to 3 to 2 to 3. That balances the electron. So there's time. I'll go ahead and prove to you that this is a net ionic equation. What's not shown here? What's not shown in the net ionic equation? What's missing in any net ionic equation? The what? Well, which ions? The spectator ions are missing. What's the spectator ion here? Well, it could be anything, right? We can make up whatever anion we want because it's a spectator. It's not involved. As long as it stays soluble in solution, they give us these ions in aqueous solution, we'll be okay. So here's an example. Here I'm using the nitrate ion as the spectator ion. But it could have been the chloride ion, or it could have been the acetate ion, or it could have been the bromide ion. As long as it's not reacting, it's a spectator ion. So now here's that same reaction, but here's the full molecular. And we can spin this the same way, right? This is iron. Let's do the full ionic. One more time, just for emphasis. The full ionic is Fe solid plus, here's going to be palladium. What's the charge on it? Well, there's 2 nitrate ions here. I did that because we know that it's the palladium 2+ cation. So palladium 2+ plus 2 nitrate ions in aqueous solution. And that's going to give us, this is Fe. Oh, I should have balanced it. Oops. Let's balance this. Let's balance this first. We've got 3 nitrates over here and 2 nitrates over there. So I'm going to use my lowest common multiple, and I know that that's going to be a 3 here and a 2 there. I'm just skipping a step, really. But once you get used to recognizing these, 2 on one side, 3 on the other, right? Lowest common. That gives me 2 irons here, so that's 2 here, 3 palladiums here. Okay, now we're balanced. So this is 2 iron solids plus 3 palladium 2 plus, and now I've got this 2 now turns into a 6. This gives us 2 iron 3 plus in aqueous solution, plus, once again, 6 nitrate ions in aqueous solution, plus 3 palladium solids. All right, there's our full ionic. Let's find the spectator ions. There's only 1. There's 6 nitrates here, there's 6 nitrates here. So there's your spectator ion, and that leaves then 2 Fe solid plus 3 palladium 2 plus in aqueous solution goes to 2 Fe 3 plus in aqueous solution plus 3 palladium solid, which is, of course, what we started with at the very, very top. Okay. So I went a little fast today because I wanted to make sure you saw the completion of this. It was a little more complicated than perhaps you're used to, but it's just because I'm using these examples to also then go over earlier stuff to remind you of that and just show you how it's all really related.